Hello everyone, I would like to introduce myself. My name is Kelvin Sobrinho and I'm here to present the paper titled Influence of Bearing Coefficients in Cold-Formed Stainless Steel Bolt Connection. This study was performed at the State University of Rio de Janeiro, Brazil. This presentation is divided into Introduction, Design Rules, Experimental Program, and Finite Element Modeling, Result and Conclusion. As we all know, there is an increase of stainless consumption all over the world. This is due to its excellent properties such as high corrosion resistance, durability, fire resistance, ease of maintenance, appearance, and aesthetics. The material's cost is high compared to multi-carbon steel grades, to the nickel contents and the traditional structural concepts where there is no consideration of the maintenance cost. In addition, the stainless steel codes are based in multi-carbon steel grade behavior. However, it's not adequate. Therefore, this work has been performed in order to evaluate the bearing coefficient influence in austenitic stainless steel bolt connection. The discussion of outcomes are based in stress distribution and force displacement curves. In addition, the outcomes are compared to Eurocode 3, Australian New Zealand Standard, American Society of Civil Engineers, and Design Manual for Structural Stainless Steel Requirements. It has been observed that there occur effect in bolt connection. This effect is related to the following: high distance found between hole and end plate. This problem can reduce the capacity load of bolt connection. The Eurocode 3 Part 1.4 is responsible for its stainless structures. This criterion is similar to what was being observed in multi-carbon steel. In contrast, the design manual proposes a similar equation if an important modification relates to ultimate yielding. Another question was addressed to classification in inner and outer plates where it was applied a coefficient Kt. AS and NZS 4673 and AC 82 standards separate the tear-out fire modes from bearing. For tear-out, the material properties in the transverse load direction is used, and for bearing, as for the manual, FU is used. However, if a fixed bearing coefficient equal to 275. In order to evaluate the structural behavior, two structural schemes have been chosen. The idea is to analyze the behavior for inner and outer plates considering the same geometries, where two values of ion 22 and 32 mm were analyzed. The connections were 3 mm thick and has a 13 mm hole, 1 mm larger than the bolt diameter. A numerical model has been developed using the finite element program Abacus. It uses solid elements, geometric and material nonlinearities were incorporated in model. The true-state concept was used. In general, the numerical models were able to represent the bolt connection actual behavior, both in terms of ultimate loads and fire modes. In the outer plate test, it was not possible to observe the peak loads due to bolt rupture. However, the model showed a similar behavior until the end of the test. In this test, it is possible to observe the curl effect even a relatively low load level compared to the numerical model. For inner plates, it can be observed that there is a similar behavior if a similar peak load. For the test with 22 mm, the numerical modes show a good agreement in comparison with the experimental test. The failure modes observed for both bolt connections was still out. The table presents a summary of the results obtained, showing a good correlation between the ultimate loads obtained between the experiments and the numerical model, except for the outer plate with 32 mm, which had an unforeseen bolt failure. Excluding this test from the analysis, a P numerical load on P experimental load, average of 0.96 could be obtained if a small standard deviation of 1.2%. This number validates the numerical mode, enabling a parametric study to be performed. The final deformation was similar for both experimental and numerical outcomes. The parametric study aimed to evaluate the influence of the curling effect on the behavior of the connection. Choose the geometrical properties of the connection varied from E1 equal to 42 mm to a value of 60 mm. In addition to the variation of the parameters, E1 on D, different thickness values were also analyzed. The verified modes observed in all connections. The difference between the connection ultimate loads if curly presents a reduction in the load capacity. The figure presents a comparison between the two investigate joint layouts. If a 3 mm plate where it can be observed that the model without curling reached a higher ultimate load, about 8%. The figure below shows the deformation of each investigate connection and each reached the load predicted by Eurocode. It can be mentioned that the alter of the plane displacement is much higher of the cases with high E1 values, and even for thinner plate. A curve was traced related the load normalized with the alter of the plane displacement, measured on the axis of the end of the stainless steel plates shown in the figure. From this curve, it was possible to observe that regardless of the connection thickness, the curl effect starts at the same load level, equal to 0.4, which is very close to the value determined by a manual for connection if deformation control, identified as SCIELS. After this limit, the phenomenon begins to be influenced by the connection geometric parameters T and E1. Connection if upper E1 and lower T presents a lower load level for the same level of out of the plane displacement. From this point, the curve if the normalized numerical load versus be measured as the displaced association if the whole elongation of the hole are present. From this curve, it was possible to observe a drop in stiffness generated by the curl effect, which was slightly more pronounced in thickness, T equal to 2 mm, which are more susceptible to the phenomenon, despite the difficulty in determining the connection ultimate load influenced by the curl effect through a static analysis. It was possible to verify how conservative the codes are in these aspects, except for AS-NZS 4673 and AC-82, which research excellent approximation for the connection without the curl effect, or in which the phenomenon did not influence the behavior. Alternatively, connection that present the curl effect or T-out value led to a safer value and using AS-NZS 4673 and AC-82. Therefore, for connection if the E1 on duration lower than 3, the manual leads to the most efficient prediction. For connection with high E1 values, where the phenomenon occurs, the code presents a high reduction of resistance with adoption of the Birkhoff's alpha B. Therefore, for this connection, the Eurocode proved to be more suitable, although the Eurocode uses a reduced ultimate strength that would lead to more economical design. For connection with T equal to 5 mm, considered thick by the manual, the phenomenon was not relevant, being similar to connection where the inner plate controlled the design. This figure presents a numerical loss normalized versus Beer curve, where the magnitude of the color factor was considered varying the load levels. This curve makes it possible to identify an out-of-plane displacement equal to 0.5 mm, as the value corresponds to the design load predicted by Eurocode, using the strength criterion. In addition, it was possible to confirm the connection ultimate load reduction due to the color factor, i.e. 8%. This study indicated that color reduced the joint ultimate load and stiffening while this connection. A high stress level in the plate crush region was also observed. The Eurocode presents a good experimental and numerical accuracy associated with the adoption of the formulate used for connection design based on deformation control, where the maximum out-of-plane displacement reached 0.5 mm. For connection without the Coulomb effect, or thick plate connection, SONZS and AC provides an excellent prediction of the ultimate load carrying capacity. Therefore, the use of the manual is suggests for connection if E1 on D ratio less than 3, although the use of the Eurocode reduced the ultimate load led to more inconsistent values. More economical results were achieved while making the use of stainless steel in structural application more competitive. New experimental tests have been performed. Thank you for your attention.